Welcome back. In this lecture, we'll continue the discussion of manipulating NumPy arrays with a focus on reshaping. We'll explain what it is, why it's useful, and how to do it. Let's get started. We'll begin by loading the dataset or datasets we want to use. This time, we'll be using load.txt to import the lending company numeric CSV file. As we progress through this section, we'll be mainly using the same 2 or 3 files. So moving forward, we will assume you know how to import and clean these arrays. If you've forgotten what the dataset looks like, here's a reminder. All right, now that we have our data, we can discuss what reshaping is when it comes to data manipulation with NumPy. Before we do that though, let's look at the big picture first to better understand why reshaping is useful. In data science, we often rely on readily available functions and methods that have specific input and output limitations. We can't always plug in whatever arrays we want and hope for the best, because certain conditions about shapes and sizes need to be met. Similarly, it isn't always possible to store the outputs of a function as a part of an existing array or series. In such cases, reshaping the array can resolve the problem. More precisely, reshaping is the act of morphing the shape of an object in a certain way. In NumPy, we'll be altering the shapes of arrays. However, there are certain restrictions to the shape we can give to an array since we have a fixed amount of data available. Fortunately, NumPy contains an easy-to-use function called reshape, which we'll explore right away. Naturally, the best way to do this is by coding. So let's go back to Jupyter. For starters, let's quickly display the shape attribute of the array, data lending numeric. The output states it's 1043 by 6, meaning this is a 2D array with 1043 rows and 6 columns. Now that we know the shape of the array, we can flip the number of rows and columns it has. To do so, simply type out np.reshape and add the dataset in parentheses. Then, within those parentheses, we also need to provide a tuple containing the size of each dimension, which will be 6 and 1043 here. The reshaped array has 6 rows and 1043 columns, but it's not a sideways flipped version of the original one. Instead of each row turning into a column, the reshaped array has taken the first 1043 values of the flattened array and placed them on the first row, then the next 1043 on the second row, and so on. More accurately, we have the 6 values from the first row of the initial dataset, lending company data. Then we have the 6 values from the second row, and so on until we place 1043 values on the first row of the reshaped version of our array, after which we'll move on to the second row. This operation goes on until the very last row of our initial dataset. That's why you can see that the final 3 values of the 2 datasets coincide. Okay, that's not something we'll often need. If we want to turn rows into columns and vice versa, we'd need to use NumPy's transpose function instead. As you can see, the output we obtained has exactly turned the rows of lending company data into columns. Right. Now, let's try to reshape the same array into a different shape, like 3 by 500. If we try this, we get a value error message explaining that we can't reshape an array with 6,258 elements into that shape. That's because the new array must include exactly as many elements as the old one. Hence, the product of the sizes of each dimension of the new array should equal 6 times 1043, or 6,258. So, if we want to have 3 rows, we'll need exactly 2,086 columns. Okay, so the total product of the sizes of all the dimensions must equal 6,258, but the number of dimensions doesn't have to stay the same. We can take this 2D array and reshape it into as many dimensions as we want. For example, we can set the shape to be 2 by 3 by 1043. This gives us a 3D array, which holds 2 2D arrays in it, each consisting of 3 rows of 1043 columns. Great! We can also artificially add as many dimensions as we want by adding 1s to the tuple. You can tell the reshaped arrays of higher dimensions by examining the number of square brackets at the very top and bottom of the array. This trick is useful when a method or function only takes inputs with a higher number of dimensions than the array we want to plug in. However, it's important to understand that reshaping doesn't immediately alter the dataset. Instead, it just returns a reshaped version of the original array. Even though we've shown several different reshapes in this lecture, if we display the array on the screen, we'll see it still has the same shape it initially had. Hence, if we want to use the reshaped version of an array multiple times, it's a good idea to store it first. All right. Before we move on, we briefly want to mention that reshape has an equivalent NumPy method of the same name. Simply type lending co-data numeric dot reshape and add the new shape in the parentheses. The output is identical to the one we see above, so using either is a matter of personal preference. Just try to keep your code consistent, so if you start using the method, continue using it throughout your entire code. Great! Now that we know what reshaping is and how to use it, we can turn our attention to another aspect of manipulating ND arrays, removing values. In the next lecture, we'll discuss how to delete values from an array. Thanks for watching.